All right. First, I wanted to give us a real quick, maybe better representation of what we're actually finding on these problems here. So, I mean, if we look at this, this is a two-dimensional version of, the intersection of two different functions. And we're saying, well, if we take cross-sections perpendicular to this that are coming out of this two-dimensional plane. So over here, we've got a three-dimensional representation of that. So if we take cross sections perpendicular to the x-axis to be squares, and we start filling this in with a bunch of squares like this, okay, this is what this shape would end up looking like. Okay, so what we're doing is finding the volume of some shape that looks like this, right, where we have cross sections. So if I were to cut this way, right, that cross section would be a square, right? So this is what that solid would look like, right? If we instead do equilateral triangles instead of a square, we would be finding the volume of a shape that looked something like this. Or if instead of cross sections being equilateral triangles, we did semicircles, we would be finding the volume of a shape that looked like this. Okay, so I wanted to give us a better visual representation of what we were actually doing. All right, so let's jump back to the notes then. I think we left off about here on example 2, where we said this was a circle with a radius of 3, centered at the origin, and we're taking these cross sections. So every single cross section is an isosceles right triangle with the hypotenuse lying in the base. So we determined that the hypotenuse had this length, right? And this is about where we left off. So our goal is to find a formula for the area of this triangle. There are a couple of different ways that we could go about this, right? We could find the height here. We could say, well, this is the base and this is the height. Or we could just find both of these sides and say that these are the base and the height. Okay, either way we want to do it. I'm going to go ahead and find the length of both of these sides. I know this is isosceles, so I know that these two sides will have the same length. I'll call them z, just so that we don't get variables confused. So if I want to use Pythagorean theorem to set this up, I could say z squared plus z squared is equal to the hypotenuse squared. So 2 times the square root of 9 minus x squared squared. So here, these would combine, right? This would just be 2z squared. And then this side we would end up with 4 times 9 minus x squared. Right, so if I'm, oops, put my parenthesis in the wrong spot. If I'm squaring a square root, that will just cancel out. Then I could divide by 2 and get z squared equals 2 times 9 minus x squared. Then if I take the square root of both sides, I get that z is equal to the square root of 2 times the square root of 9 minus x squared. So if both of those sides have a length of the square root of 2 times the square root of 9 minus x squared, I can say that the area here, I can write an area formula, so a of x equals 1/2 base times height. But what we've found is that the base and the height are both this length of z, right? I can say that both b and h are the square root of 2 times the square root of 9 minus x squared. So I can say this is 1/2, and I'm just going to write it as square root of 2 times the square root of 9 minus x squared, all of that squared. So if I square both of these, if I square the square root of 2, I get 2, and if I square the square root of 9 minus x squared, I get 9 minus x squared. So 1/2 times 2 then is just 1. So what we end up with is our area formula actually turned out to be fairly straightforward. Right? There was kind of a complicated setup, but the area of every single one of these isosceles right triangles is just 9 minus x squared. So now I'm integrating from x equals -3 to x equals 3. So let's scroll down a little bit here. So my integral then would look like this, -3 to 3 of my area formula, so 9 minus x squared dx. Okay, and this one's pretty straightforward to do by hand. Take the antiderivative, so we would get 9x minus 1/3 x cubed, and I want to evaluate this from -3 to 3, so I'm going to plug in 3, so I'll have 9 times 3 minus 1/3 times 3 cubed minus, and plug in -3. 9 times -3 minus 1/3 times -3 cubed. So when we evaluate all of this, I think we could take a minute to try to work this all out by hand, but I think if we just plug that into the calculator, we end up with 36. And remember, if this is a free response question, we could stop at this step right here. Okay? But what we found is this volume of this weird looking shape would be 36. All right, let's try the last example then here. So we're saying that we've got R is the region bounded by the graphs of x equals y squared and x equals 9. So here we can think about this two different ways. We could anti-differentiate with respect to y. Okay, we looked at examples of area like that. But here I think it might actually be easier if we just solved this for y. So to do that, I would take the square root of both sides and just say y equals plus or minus the square root of x. So again, let's kind of sketch out a little picture of what's going on here. So why don't we get some nice axes here? All right, so square root of x looks like this. Negative square root of x would just look like this then. And my other line is x equals 9. So this vertical line right here. So what I'm looking for is this region right here. This is the base of my solid. And then I'm told that every cross-section perpendicular to the x-axis is a semicircle. So we want to find a formula for the area of this semicircle. So let me sketch out my semicircle. Now, the distance between the top and the bottom here, well, the distance from here to here would be the square root of x, and the distance from here to here would also be the square root of x, right? If I'm saying this is positive square root of x and this is negative square root of x, I'm just saying, well, square root of x minus negative square root of x would give me that that distance is 2 square root of x. So the diameter of this semicircle is 2 times the square root of x. So my radius then, okay, we can just say the radius would be half of that. Radius would be the square root of x. So the area of my semicircle is 1/2 pi r squared. My r then, half of the diameter, is just square root of x. So my a of x, my area formula for all of these cross sections, is 1/2 times pi times the square root of x squared. And the square root square root of x squared is just x, right? So we get 1/2 pi x. So then we need to set up our integral. Okay, well, we haven't talked about the bounds yet for this one. Obviously, I would be starting at 0 here, and then this bound here, well, I'm told that this is the line x equals 9, so my other bound is 9. So I will take the integral from 0 to 9 of my area of the cross-section. So my area is 1/2 pi, and I can pull that 1/2 pi out front because that's a constant, a coefficient. So I'm just taking the integral then of x dx. So the antiderivative of x is 1/2 x squared, so I'll have 1/2 pi times 1/2 x squared, and I want to evaluate this from 0 to 9. So this just ends up being, so I can multiply those 1/2s together and say that this would just be pi over 4 times 9 squared minus pi over 4 times 0 squared. So 9 squared is 81, so we just end up with 81 pi over 4. So what we found there was the volume of this figure, if we think about cross-sections coming out of our paper here, our semicircles. All right, so that's it for this note sheet. Tomorrow in class we'll do a few more examples together and then have you guys try some on your own.